Thomas Jefferson National Accelerator Facility is a laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live,
Good evening. Welcome to Jefferson Lab's Science Series program. My name is Lisa Searles Law, and I work here in the education group at Jefferson Lab. We have the pleasure tonight of hearing from Scott Winters. He is a NASCAR driver and winner of the Sun Belt Regional in 2002. He also works as an engineer at Lawrence Livermore Lab, and he works on the National Ignitions Project. So tonight he's going to be combining two of his passions, and he's going to be presenting the physics of stock car racing from a NASCAR champion's perspective. Help me welcome Dr. Winters.
So I guess to start off tonight, I just want to say I'm excited to be here. I'm from California, born and raised in California, and I've followed NASCAR for a long time as a fan in addition to being a driver, and I'm excited to be able to talk in a great state of Virginia with some super tracks like Martinsville and Richmond around the corner. The other thing I just wanted to mention is maybe just by a show of hands is how many people have been out to the Langley Speedway. So a good portion. So I won the 2002 Sun Belt Regional Championship, and right in your own backyard, you have a regional champion by the name of Mark Wartz, who won the 2003 Southeastern Coastal Championship. So it's pretty impressive. So let's get started, and we'll talk about the physics of stock car racing. So first, what I want to do is just spend a few minutes and give you a little bit of background on what I do at Lawrence Livermore National Laboratory and some of the things behind that, because I'll be relating some of that to the physics in my NASCAR racing. And so I guess to start off, I just want to say that I have my PhD in engineering. I've worked at the laboratory for about 11 years. And currently working on the National Ignition Facility project. It's the world's most powerful laser, and currently has 4 beam lines. We'll then go up to 192 beam lines over the next 4 years approximately. Its peak power is 500 terawatts, which is a lot of power. So let me just run a video here and give you an overview.
The National Ignition Facility, or NIF, will focus up to 192 laser beams onto a tiny target inside a target chamber. This will create fusion in the laboratory, similar to what occurs in our own sun and other stars. Other fusion conditions have been created in the past in underground nuclear weapons tests. Although nuclear tests were stopped in 1992, a strong nuclear deterrent remains a cornerstone of the United States national security. Today, it's the job of the Department of Energy National Security Laboratories to ensure the safety, security, and reliability of nuclear weapons. NIF will help validate the nation's stockpile by verifying computer simulations, as well as gain knowledge towards harnessing fusion as a clean, efficient energy source. This overhead view of NIF shows how the laser beams pass through the amplifiers multiple times before they are transported to the target chamber. The first pulse of light is generated near the center of the facility, known as the master oscillator room. The light is divided and carried through optical fibers into the main laser system, where it is amplified to the very high levels required for experiments. Next, the beams travel to the other end of the building, where they enter the 30-foot diameter target chamber as ultraviolet laser beams. Here, the beams converge on a target the size of a dime, which drives the fusion ignition process, all of which happens in less than 1,000th of a second. A critical part of making NIF work are the thousands of large optics that focus, convert, or reflect the light inside the laser enclosures. Some of the optics are made from giant crystals that are grown in special fast-growth tanks, then sliced into optical windows. These and other optics, such as this purple laser amplifier slab, are first cleaned and coated in a special optics processing facility. In a separate optics assembly building, mechanical components are cleaned in the world's largest ultrasonic cleaning tank. The coated optics are assembled into modular units and placed inside canisters to protect them from contamination. The canisters are picked up by robotic transporters that carry them into the laser bays, where they are inserted into the laser beam lines. NIF will be the largest laser ever built, and is a key component of the nation's stockpile stewardship program.
Great. So that gives an overview of what NIF is, and what you saw some of the optics there. I'm responsible for doing some of the alignment of those optics and really making sure that the beam gets aligned on that itty-bitty target you saw in that video. So it's very exciting, and I really enjoy that aspect of it. So next, I'd like to talk a little bit about my racing background. I've actually started racing when I was 8 years old. My parents got me into go-karts. I raced a handful of years competing locally and nationally, and then got into NASCAR racing. And so, like I said, in 2002, I won the Sun Belt Regional Championship. And just to give you a little bit of an idea of what I race, I'll show you this video.
Regional Championship. NASCAR Weekend Racing Series presented by Dodge, Sun Belt Region Champion, Scott Winters.
Okay, so basically today what I'm going to be focusing on is the physics of stock car racing. And again, I want to throw in from a driver's perspective. I want to give you a flavor of from me being an engineer, and also and relating to the physics, also from the driver's perspective, some aspects of that. So I'm going to cover some areas such as tires, mechanical suspension, aerodynamics, engines, and lastly, I want to talk about the driver's input because that's clearly a very important aspect of the overall race car and being able to win races. And although, I'm saying it's stock car racing because things we're going to talk about today apply to, in general, all of stock car racing, a lot of the things I present are going to be some video and footage from NASCAR, from the weekly racing series all the way up till the Nextel Cup series. You'll actually see in some of the pictures where I have some outdated stuff and it says Winston Cup. So to start off with, when we talk about the physics, it's important to understand that the physics is very old, meaning that hundreds of years ago, there's been physicists that had the understanding of what was going on, and it's really been, and so that has really not changed over time, but the engineering behind the race cars is what changed. And so I want to show a couple things because it's interesting just to compare, to think about for a second. Wow, the physics here hasn't changed, but why are things so much different?
The roots of stock car racing can be traced back to the southeastern United States in the 1930s. Small-town speed demons carved tiny dirt tracks out of farmers' fields, and on weekends would fire up their family sedans and race for bragging rights. Before long, promoters became involved in the fledgling sport. One of the first was William Big Bill France. He staged races on the wide beaches of Daytona on the eastern coast of Florida. Cars would run almost 2 miles up the beach, make a wide, sweeping turn through the dunes, rocket down the coastal highway, then turn left back onto the beach. In 1940s,
So pretty amazing when you look at what was done back there and to say, the physics that influenced those cars are no different than the physics that influence the cars today. And so then we just snapshot, which everyone will see very familiar.
Take 30,000 horsepower, more than 100,000 screaming fans. Mix it up at 200 miles per hour. And you've got the recipe for NASCAR.
Okay. So to kind of start off, what is the goal of every stock car team? And the goal is to optimize their car's performance within the limits of physics, which we're here to talk about today, and clearly the rule book. And so when you say, okay, we're going to follow the rule book, then we'd clearly want to be able to push the envelopes of physics and achieve the best performance we can. And so today, as I mentioned earlier, I want to talk about these 4 areas: tires, the mechanical suspension, the aerodynamics, and engines, and again, I'll talk a little bit about driver's input and a couple other things. But the thing I wanted to point out here was if you go back and you look at, well, when were some of these discoveries first made, and who really influenced it from a physicist perspective. And so if we start off with Henry Coulomb, and although things have evolved, this is really the first physicist that did significant work in terms of frictional, of sliding surfaces and rolling surfaces. And so you can see he did his most significant work back in 1781, clearly a long time ago, and things have come a long ways, but the basic physics of this problem was done back in that time frame. From a mechanical suspension perspective, and again, I'll be showing some details on all this, but I think the primary thing here is Isaac Newton and Newton laws that really drive that. And so that was done in 1687, and he had the 3, his first, second, and third laws, and made significant contributions there. Aerodynamics is not quite as straightforward. There's been a lot of work done there. Some of the early work, and actually the word aerodynamic was not used until 1837, and so we use that word today. But actually, some early work in that field, Leonardo da Vinci did very early in the 1400s, and then I listed here some of the other contributors since then. Modern day aerodynamics, they really, Cayley here in 1804 is someone they really tie to who who really kind of they view as the grandfather of establishing aerodynamics. And then lastly, the engines. And the perspective I'm taking here, clearly there's mechanical parts and all that with engines, but when you think of it in terms of the physics, is really the four-stroke system. And Rochus invented that four-cycle approach. Otto had really built the first internal combustion engine with that concept, and so that's why I show. So it's interesting to look at the dates here, the 1700s, 1800s, that all of this work was done, and it's just been evolving within engineering ever since. Okay. So the first one I chose to talk about are the tires. The by far, and clearly, depending on if you're talking about a short track or you're talking about Daytona, and you're talking, there's some different things or different emphasis is placed on areas. But I think by far, no matter what type, you're talking a short track, a dirt track, super speedway, tires are a very big factor. I mean, tires are the only connection between the car and the ground. So just from that perspective, and thinking about Newton's law, that the first law, that if something's moving in a line, that it's not going to change its path unless acted by on an external force. And so the tires are unless clearly someone bumps you or something like that, tires are what are going to actually allow that to happen. So some general observations. So we all know tires are compliant, and the important thing is they develop forces nonlinearly to their normal load. And so there's this relationship which Henry Coulomb established, again, back a couple hundred years ago, saying that the force capability of an object, in this case we talk about the tire, is proportional to the coefficient of friction and the normal load on that tire. And so I'm just going to show a little clip here of some Winston Cup tires.
Mandates 15-inch tires, which are much wider than passenger car tires, but narrower than the tires seen on most open-wheel racers. The tires are completely smooth with no tread, and provides the most contact with the track, the most.
So I'm just stopping that for a second. It's very interesting. Tires themselves are very complicated. The mechanism that is used to represent, we have this very simple equation here that represents the amount of lateral force or amount of force a tire can generate, which is proportional to the normal load. But it's very complicated, and so this coefficient of friction factor that you get from the interaction of the road to the rubber is actually quite complicated, and some very early physicists never thought the race cars would achieve the speeds they achieve today, because they didn't ever think that this coefficient of friction or this parameter could be as large as it is today. So you'll see in here that I should mention this, is that I've taken I've got some NASCAR footage. I've pulled out some graphics from various magazines, some other websites which I've highlighted or give reference to where I've pulled them out to really talk about some of these issues. But there's a great source of information that racers, the average fan, can get about the physics of racing and a lot of the things we read and have easily available to us. The point I wanted to make about these, again, just emphasizing the tires, and I have a few more slides here to talk about that, is that there's four primary factors, and you can break some of these up a little bit differently. But basically, as I talked about before, the vertical loading, the contact patch, the chemical makeup, and the temperature of the tire, and what they call the angle of attack or slip angle are parameters that influence how much traction or grip a tire develops. And so I know you can't read some of these details on here, but I want to just show some of the trends and give a little perspective on. So this here is basically a graph showing how much lateral force a tire has on it versus slip angle. And the important thing I wanted to show here is that, and so you can think of this as the driver's steering wheel input. It's not exactly that, but you can think of it that as in a way. But as you push a tire and you start getting more and more lateral force, you start coming up this curve and getting more, so you can have larger and larger accelerations. And at some point, you hit a maximum and then you start falling off. And so some top-notch drivers will figure out a way to run right at that point. So they'll be able to run their cars. If you look at, you take Ryan Newman, for example, right? Ryan Newman is extremely fast in qualifying and clearly racing too, but he's able to out-qualify people consistently. And so why can he do that? Well, clearly he has a superior car, but he's learned too as a driver to be able to drive in this regime. And you can see if you push it too hard, then you start falling off and you actually get less traction from the tire. Now, one point, jumping over to this other graph that I want to make, is that when you do push a car to the limit, if you start sliding the tires too much, you'll start increasing the temperature of that tire. And so the tire grip is also a function of temperature of the tire. And to a certain point, again, the hotter that tire gets, you'll actually increase the grip to some point where you actually exceed that. You get the tires hot and the grip actually drops off. So there's a fine line of running right at the ragged edge and not overheating the tire. And then lastly, with this graph, I just wanted to point out about the non-linearity of how much lateral force a tire can generate versus the normal load on a tire. And the point is it's nonlinear. Okay. So this view graph and the next one is going to illustrate this point a little bit. Is again, the tires develop forces to make the car turn. And clearly slow the car down on corner entry and accelerate the car on corner exit. And so again, all you have is between the car and the ground are those tires. The front tires contribute towards turning and braking. The rear tires contribute towards turning, braking, and accelerating. And I have a little better graphic to show that on the next slide. But there's this thing called the friction circle diagram. And basically what it says is that a tire can only generate so much traction or so much ability to turn or accelerate the car. And so if you're using it to accelerate the car and you're maximizing the acceleration of the car, well, you've left no ability to turn the car without the tire slipping. And so it's important to realize when a tire is used is if you're trying to accelerate and turn, there's only so much capability that tire can offer. Okay, so this graphic here illustrates that a bit more. And again, I took these pictures. System already did a nice job making the pictures from Doug Gore. So what this shows is kind of five primary locations on a racetrack that a car will undergo. This position here is basically a car strictly accelerating down the straightaway. This position here represents a car straight line braking into a corner, and then a car just braking, and then all cornering, and then accelerating. And so really the key I wanted to point out here is that when teams and the drivers utilize this effectively is that here all that tire's having to do is generate forward bite or forward traction. And so on a lot of short tracks, you take Martinsville, for example, the teams are going to run a gear in that car so they can maximize their acceleration down the straightaway. And they're trying to get as much grip at this point. They're not using those tires for anything else but just accelerating them down the straightaway. And then you notice the front tires, although it's neglected in this case, there's clearly rolling resistance that's associated with them, but there's no large forces per se. In this figure here, where a car just begins to brake, you'll see that it's using forces on the front tires and the back tires to brake. And then if we jump to this one, where the car is starting to turn, you'll see no longer is it just using a braking force that's parallel with the axis of the car. It's also trying to turn the car, so the tire has to develop a larger force in that component. So the end result is that it's developing the same type of resultant force. And so you kind of step through these, and again, at different points on the track, you can, depending on how the car's set up and how the driver's utilizing it, you can either kind of optimize at various points. There's an optimization, meaning there's compromise. And also that you can look at doing things to your suspension to get the best optimization of this. So every racer, from some dirt track to people racing at Langley to racing trucks or Winston Cup, all cars respond this way, and the teams are having to deal with it and try to do the best they can. Okay, so the next step regarding mechanical suspension. As I said earlier, really Newton's laws really dictate what's going on here. And this is where I said I've got some old stuff with Winston Cup on there. But basically, the key here is there's a lot of moving suspension parts on a stock car. And so this graphic here shows a little bit of that. You know, it shows the upper and lower A-arms, and it shows the rear axle with the springs and so forth. But there's a lot of parts, and you can see some more of those details here. But there's a lot of parts that clearly move. And when anything moves, it's gonna move as Newton's law says it moves. So you basically, you know, for things that are moving in a linear fashion, you have force equals mass times acceleration. And for rotational things, you have torque equals I alpha. And those can be expanded in various forms, but in the simplest sense, that's what you have. And so you'll see where teams go through, and they'll try to make things as light as possible. They'll try to make things have the lowest moment of inertia. And so basically, you know, they're working on things where mass and this inertia factor here, and when they make their A-arms, when they do things with the suspension, they're trying really to minimize those so that it doesn't take as much force to accelerate the car, and vice versa. If there are accelerations, the forces aren't as large. So there's quite a few things that teams are capable of adjusting. Again, they build these cars so that they're optimal in a physics perspective, and they also allow adjustability in them. So, you know, as a general overview, you know, they may make changes to the springs, the shocks, the sway bars, the A-arms, the Panhard bars, many things, and all those, which is an important point, all those things are done to help the tires, to actually balance the loads on those tires. That's why the majority of these changes are made. So let me just show a little clip here on an adjustment that some cars will make.
One adjustment is called wedge. The wrench is inserted near the rear window, turning a long screw. This increases or decreases spring tension and changes the weight distribution of the car. Another adjustment is called the track bar. Like wedge, it helps adjust how easily the car turns in the corner.
Okay, so the next thing I wanted to talk about was aerodynamic forces. You know, so those are very critical at the short tracks. Again, using Martinsville for example, it's not that important. The things that I race, aerodynamics aren't that important. They're still a factor, but they're not that important. But clearly, the big tracks, when the speeds go up, they're extremely important, such as Daytona or Talladega, even some of the high-speed tracks like Atlanta. So the thing I wanted to point here, there's two primarily aerodynamic forces that the teams are concerned with. That's referred to as drag and lift, or in terms of the in general nomenclature they use that, but in NASCAR we want negative lift, we want downforce, and so the two things that the two equations that drive that are shown here in a simple form, and the important point I want to say is as they're basically a function of the velocity squared. So as the speed goes up, if you double your speed, you actually increase this force by a factor of 4. So it's very dramatic. If you're running at a speed that has an average speed of 100 miles an hour, the influence is not as significant as if obviously if you double that and you're doing something close to 200 miles an hour. The other important point is that teams will work with is the drag coefficient, which is this term right here, and the coefficient of lift or downforce coefficient. Those two are related, so you can't just work on one and think you can get the best of both worlds. So there's a trade-off between those parameters. So here's a couple pictures. So a lot of testing's done. Modeling is extremely difficult. At the laboratory we have computational fluid dynamics modelers. We model a lot of things. In the end, doing a test is very important. And in NASCAR, I don't think there's not very much modeling going on, but there's a lot of testing that goes on. And so testing takes place at a few different levels. There's full-scale type testing, which is kind of depicted by this. So they'll put the cars in these wind tunnels. And there's also smaller models, 40% scale stuff that's done. And again, they're looking at drag and downforce. And so you see here in this depiction, there's actually a moving floor here, and this is actually a really nice setup. This facility here is well, I guess both of these are in the North Carolina area where this work is being done. I had just to mention, I had the opportunity today to go to the Langley Wind Tunnel and got a great tour there. Saw one of Rusty Wallace's cars, and it's pretty impressive how big some of these wind tunnels are, and again the physics and science that goes into the work for characterizing this important parameters. So again, just to say, okay, well, what kind of things do they look at when they do wind tunnel testing?
Test the cars extensively before committing them to race. Aerodynamic engineers test the cars in wind tunnels like jet aircraft. The object is to make them slice through the air, but still maintain the proper amount of downforce, which gives the cars traction.
So it's the changes that we see on TV and even the changes we see in the garage are very slight that have influences and influence what the drag and downforce components are. So why? I guess this other clip I'm going to show you, I wanted to put on here just to show the significance of the aerodynamics and what happens in drafting.
The drag. As a car goes through the air is forced around and over the body, leaving a void behind. Trailing cars pull it.
So I wanted to show something here. Is you'll notice before this car gets up here, you'll notice that the flow over this car basically drops down. So you have in front of this car you have a high pressure zone and a lower pressure zone back here. When this car pulls up, you'll see the airstream go through, and so it's really allowing the coefficient of drag of this car to decrease, and because this car doesn't have the high pressure here, it's allowing its effective drag to decrease, so the two cars together go faster.
Into that void and push of air against the front car. Two or more cars can therefore go much faster than a single car.
Okay. Okay. So again, back thinking in the terms of the tires are the most important thing, and the goal every team has is to get a balanced setup in their car. And again, they're trying to balance the forces to optimize the maximum available traction. So this clip here, although it cuts off a little bit, this clip here talks about a loose versus tight setup. And then I'm going to show a graphic here of something that's clearly everyone will agree this is a loose setup.
A car that tends to oversteer in the turns is called loose. A car that tends to push up the track or understeer is called tight.
So from my perspective, from a driver's perspective, typically a race car that's a little on the loose side will be extremely fast, but it's much harder to control, and you're more on the edge. I think since I've never driven the big speedway tracks, they're much more conservative in terms of keeping a car a little more on the tight side than loose side versus the short track racing that I'm very familiar with. This next clip here will show a car that's loose.
Control. So anyway, that clearly Dale Jarrett did not like that, but
it clearly showed where that car got loose for whatever reason. But my main point is that when we're balanced, when teams are trying to balance their setups, that they need to equally utilize the traction in the front and the traction in the back, and to get that balance set up. Okay, so the next step is when I've gone down that list is now that's all in good. You know, you've got to be able to generate the traction. You've got to have a car that handles, but boy, you better have an engine that pushes that thing down the straightaway, or you're not going to beat the other teams. And the key here is you know, all these teams build engines to produce power. Clearly, they want to have the fastest thing, but it's important that they have sufficient reliability. They can have the most power in the world, but they need sufficient reliability to finish a race.
Power plants for the cars are restricted by NASCAR to 358 cubic inches and may use only one 4-barrel carburetor. No fuel injection is allowed. That forces these engineers to find power in other places, and they do. A Winston Cup engine produces over 700 horsepower and turns more than 9,000 RPM.
Okay, so a graphic here on the engine. You know, again, the engine power is used to accelerate the car. I talked about Newton's law, F equals ma, and so you know, all the power to do that, to accelerate the car, is coming from the engine, and it's really doing that to overcome two primary forces: the aerodynamic forces, which can be quite large, as I said earlier, as a proportional of velocity squared, and also rolling resistance. So the power generated is one representation of that is the power is equal to force times velocity. And an important thing to point out is that when you think of aerodynamic drag, power is proportional to the velocity squared. So the reason at the very high-speed tracks, you know, when they cut the power in the cars, when NASCAR mandates this restrictor plate to cut down the speed, you know, because aerodynamic drag is a function of v squared, that they're able to accomplish that pretty easily. Again, the thing here with this graphic is that I talked earlier about the Ottawa cycle and the four-cycle approach. It's you know, from the physics perspective, although there's a lot of mechanical stuff going on, you have a thermodynamics problem of getting, you know, air in through here, mixing that with fuel, and then having an exhaust come out. And so all the potential power available to you is in that air-fuel mixture that you put into this device, which obviously we call an engine. But that process is going to determine how much, and all the fine-tuning you can do here is going to determine how much power you can generate. Okay. So with the, you know, the car optimized, you've focused on your tires, you've looked at the aerodynamics, the mechanical suspension, you've got a great engine. Clearly, the driver is a very important factor. And during a race, which we've all seen on TV, during a race, you know, the driver is the only feedback, and really the best feedback. So it's pretty remarkable, and I think about it in terms of working at the lab, and we have all these control systems that control this, you know, very complex machine. But by far, you know, the human is a control system that we just can't duplicate with computers or machinery. During a race, you know, or just in general while driving, you know, there's many features that a driver is trying to deal with. You know, they're using many of their senses to understand what the car is doing and trying as best as possible to give feedback to the crew chief to make adjustments. So I guess, yeah, my point here is you know, they're using their vision, their smelling, their hearing, feel and emotion, all of those things to give feedback back to the crew chief to allow cars to be adjusted. Another important point, you can have a perfectly good setup car that is optimizing the physics, and a driver can go out there, overdrive the car, be jerky, and really exceed the physics limits and hurt the car's performance. So it's a fine line between having the input from the driver allow the car to perform at its peak, and also then meeting that maximum performance.
Benefit from onboard computers or traction control devices. It's all about feel and guts. Each lap, drivers slam into the turns at breathtaking speeds, pushing the car to its absolute limits.
So again, just to say a little bit more about this is it's very interesting to from my perspective, we have these simulator games that you can anyone can play. You've got the NASCAR that you can play on your computer. It's very interesting. So when I play that, one thing that I really struggle with is the feel and motion side of it, because there's no feedback of what kind of the seat of the pants feel. You clearly have your vision there. You don't have any smelling, and you can hear some things going on. But really, all those factors contribute into what kind of feedback a driver can give, what kind of feedback can he generate to get the best performance in the car. Okay, so as my last slide here, I just want to make some general comments that the team that best understands the physics that influence their race car will have a big advantage on their competitors. And you combine that with a top-notch driver, and there's no question the driver plays a big role. But a top-notch driver and a pit crew, as we've all seen, a race come down right to the very end, and the crew that gets the team out first is going to win the race. So they play a big factor too. But you put all those ingredients together to get a winning combination. Now, in my estimation, and these could vary a little bit, but from my perspective, although any of these can cause a race to be won or lost, on average, week in, week out, I believe it kind of falls in this range for importance of what influences getting the winning combination. The race car I view is about 80%. So getting the race car right in terms of tires, the suspension, the engine, the full program, I feel it's about 80% of the total package. The driver, I think, is about 15%, and the pit crew is about 5%. Now, you flub any of these up, and you can clearly not get to the end. Pit crew can screw things up, the driver can wreck the car, or the race car can just not be set up right. But you take any top-notch driver, put him in a sub-standard race car, and he's just not going to win in general when racing against very competitive teams. So anyway, that's my talk for tonight on the physics of stock car racing. I hope you enjoyed it.
Who have questions for Dr. Winters. So we'll field a couple of those now, and then I believe he will be around after we finish for a moment too.
Are you going to hold the microphone up? Or?
You want to do the picking, or you want me to?
Either way.
Okay, let's see. We have a gentleman here in the front.
Okay.
Quick question, are you still competing?
Yes, yeah. The question is, am I still competing? And the answer is yes. Let's see. We have not. The team I drive for is building new equipment for this year, new engine, new chassis, and all that. And actually, I got fitted to the race car a couple of weeks ago, and we should be testing maybe even this weekend. So.
What is the range of coefficient of friction between the rubber and the asphalt track, concrete track?
Yeah. So if you look at standard materials, just to add a little bit to that. Let me just. The question is, what is the range of the coefficient of friction between tires and the asphalt track? That's the question. If you look at standard materials, steel on steel or steel and Teflon and stuff like, typically all those are somewhere around 0.3, 0.5, somewhere in there. And when you go to the coefficient of friction for rubber, it's somewhere greater than 1, and it's as high as maybe 1.5, 1.3, 1.5, somewhere in there, but it's in that kind of ballpark range. Yes? That's correct. Just a smooth surface. That's right. So the question was, about the tires, and do the tires have tread, or if they're just smooth? So actually, with the tires designed that way, it actually allows the tire to have more what we call a contact patch. So there's actually more surface area in contact with the asphalt. And it actually makes it feel, from a driver's perspective, it's very much more controllable. You feel like you really have control of the car. When you start going to some other tires, and I've raced on treaded tires also, when you race on those, the car feels much less stable, and you've got to work a lot harder to do that. Yeah. Yes.
Why is that? This friction force is independent of area.
You know, yeah. So that's a great statement. If you look at the fundamental equations and you look at the equation I put up there that said force, and let's just use the term proportional right now to some coefficient of friction times the normal load. The basic equations that define that say it's independent of area. But if you look at experimental data to look at the various experimental results, it shows more that it's more of a function of area. Although those basic equations are not in agreement in that sense. So I can't answer the question any more than that. But that's yes.
Do you use any kind of data acquisition equipment or instrumentation? And if so, what do you consider like your key measurements?
Yeah. Let's see. I did a test for Dodge and Bobby Hamilton Racing at Nashville Speedway a couple years ago, and in that system, we basically looked at actually a series of parameters. The data acquisition system that was set up, and this was a Craftsman truck. The data acquisition system that was set up on that basically gave feedback on steering wheel input, brake input, throttle position, shock travel, shock velocity, and some various other accelerations. Your question was, of all those, which one do I think is the most important? I think, what's that? The time? The clock at the end? Yeah, well, that's clearly a very important one. I guess I would probably say I would be very interested in throttle position as a function of where you're at on the track. To see how well a driver and how well the throttle's being used, especially in situations where you know, at most cars, you take the Winston Cup cars and you look at them at Martinsville, the teams can't generally use they can't just mat the throttle down and accelerate. They've got to be very easy on the throttle, and so having that feedback is very valuable. But it's difficult to pinpoint just one in general. Another question? Sure. Stagger,
Big argument years, you talk to the older guys, we predominantly run late model class. More preference to you?
Yeah, so,
Or rear stagger?
right. So from my perspective, and like you say, you'll get, there's a lot of ways to kind of peel the onion and get there. From my perspective, what I tend to do is, and it really depends on the type of rear end you're going to run, if you're on a Detroit locker or a spool or something like that. But from my perspective, based on the track side, and it depends on the tire availability, what tires you can get and that, but based on the track dimensions and the line you typically run at that track, I personally like to calculate what the perfect stagger would be. So if you have a certain radius, the outside tire has to travel further, so it needs to be a little bit bigger, but you can calculate what that is. From my perspective, I actually will calculate that on a given track and then stay with that number and adjust other variables on the car so that it's just one less variable that needs to be adjusted. I tend to, a race car has many things that can be adjusted. I tend to try to simplify the problem because it can be very complicated for anyone. And at the work at the National Lab, that's what we try to do. We simplify problems to make them to make them simple so we can solve them. In this case with the race car, I try to eliminate as many variables as possible. So I do that calculation. I figure out what stagger would be ideal, and then I run that stagger and I make sure I don't change that stagger and I adjust other things on the car.
And go ahead and let people leave who need to leave. And I know some of you have individual questions you want to ask, so let's give Scott a thanks. Okay, before you leave, since we have such a great attendance for tonight, we want to let you know that our security guards have opened our back gates, which also open onto Jefferson Avenue. So please follow the direction of the guards to get you out of here as quickly and safely as possible. Thanks.
How you doing?
Thank you very much.
Good.
Let me ask a question. This year they've had Goodyear just change the
Yeah,
tire
yeah,
composition.
right.
How does that affect? What were they doing there?
Yeah, they were changing. Sure, great. You know, they're changing the chemical makeup of the tire, so it's